All right, let's get started. So the main goal of this lab is to set up the environment of electric VLSI and LT-SPICE. You probably have used LT-SPICE in the past, maybe in circuit one in analog circuits. So LT-SPICE is it's a free SPICE software that we can use, and there's a way to integrate LT-SPICE into electric VLSI. So if you are looking at this kind of window with the symbols like resistors and the transistors on the left hand side, so this environment is electric VLSI. It is a free backend design VLSI design tool that I can use. It's a very good learning tool. However, it's not an industry standard design tool because it's not able to integrate all these advanced nodes. So the nodes are, for example, like 5 nanometer nodes, right, from TSMC. So there's just even a PDK can be put into electric VLSI. So that's the issue. However, it's a very good practice or learning tool for beginners. So let's work on electric VLSI for A labs, and then we'll move forward with cadence. All right. So I have fundamental cadence tutorials over here ready. I got 6. I'll let you get it done in a day. Just kidding. 2 weeks probably. Take a look at it. It's a totally different environment. Black. Looks so awesome, right? Industry standard. All these people in Apple, Qualcomm, Broadcom using Cadence. So this is called Cadence Virtual. So it's the same, very similar environment compared to electric VLSI. It's just purely manually laying out transistors into the environment. However, there's another one which is even more awesome. I think we're the only one in Colorado doing this. It's Genus and Enormous because of the IP, the NDA. I cannot post all the tutorials here. Eventually, after signing NDA, there will be another 18 tutorials waiting for you. And let's get it done. So eventually, starting from Verilog, RTL, and convert everything to a chip. So we are not getting to the RTL because that's something for the front-end engineers to do. So we are back-end engineers for the VLSI class. We are back-end. But for the embedded, you guys are front-end design engineers. So two different groups in the company working on same project. So let's come back to electric VLSI. The first lab is basically just setting up the environment. Okay. You can see that if you download it, you can find out it's already lab 2 because I deleted lab 1 because you guys already know how to use the LT-SPICE, right? So there's no fundamental simulation work on LT-SPICE. I'm going to show you some examples today, but we're not having a week to just working on LT-SPICE. It's a waste of time. Okay, but I can show you some examples. So this lecture is recorded. You can review it after the lab if you need. So don't get confused, okay? It's showing lab 2, but however, it's lab 1 for this semester. Load the libraries. The library will be able to be downloaded from these links. So these are modules, like what we exercise in the embedded system. Remember, there are modules. These are modules in integrated circuits. However, these are just IDU modules. These are not real ADCs and DACs. The DAC is fine. It's a real resistor with the symbols of the resistors. But the ADC is just an ideal ADC. It's not fabricatable. Okay, just the ideal symbols. Just switches, sampling and hold. Here's the LT-SPICE code. If you have questions, feel free to ask during the lab. Okay, I'm going to run several LT-SPICE simulations, try to let you recall these commands after this lecture. Okay, really quick. And for your report, you have to run simulation and show the diagram like this. So you can see the blue one. The blue curve here is the ideal analog input. It's a sine wave. And the stars, the signal with the stars is the one getting digitized. So you can tell it has errors because you don't have infinite number of bits or resolution for the ADC. So you're getting errors because of stars. We'll learn how to calculate all these errors for the ADCs later, okay, in the class. So you get errors. That's why when you convert all these inaccurate digital outputs into the DAC and convert it back to an analog signal, it shows something like this instead of ideal and smooth sound wave. So let me ask you a quick question, very simple. Is V out here the output of ADC or DAC? V out here is the output of the ADC or DAC? Why? DAC, right? Okay, because ADC's output will be digital signals with 10 bits, right? It's just the static voltages. Okay, cool. So be ready for the quiz on Friday, right? For the DAC calculation. So for the DAC calculation on Friday, you just have to show all the steps of the Thevenin's equivalent and superposition to find out V out. So I'm going to give you a random input value for the DAC, and then you calculate for the output. All right. These are resistor symbols in electric VLSI. So you can build a DAC. Here's the DAC. So put the DAC in the symbol. So you design the DAC circuit, and then you put in the symbol, just showing all the ports. Okay, don't forget to run DRC check. Let me show you. DRC, design rule check, right? So design rules, which is here. So your report has to show 0 errors, 0 warnings. It's passing DRC. Make sure it passes DRC. Okay? The tutorial tells you how to do a DRC check, just one click. And eventually, after you show this, the next step, the task 3, will be a RC circuit simulation. That's what we cover in the Monday mainly. Look at this. How do we run a RC circuit simulation for the DAC? For the DAC. What's happening here? Why I'm grounding all the other signals, but only leaving B9 for a signal, so receiving a pulse. Yes, yeah, that's right. So I'm not using all the rest of the circuits, right? I'm grounding all of them. So if I'm giving 0 to all the other bits, it's contributing zeros. So basically, it's not doing anything, right? You can do all these parallel circuits and eventually convert it to just 1R, right? So it becomes this, right? If you ground all the other signals, it eventually becomes this. And then you connect capacitor to the load, so the equivalent circuit is exactly this one, even though it's a DAC, but it's eventually this circuit, right? And like what we did in the quiz, we convert it to its Thevenin's equivalent in order to calculate 0.7 RC. So this is asking you to verify that theory, right? 0.7 RC. So this is something I want to draw here. Because I'm simulating, so after the quiz, some students had this kind of question. Are we looking at 0.5 or 50% of the voltage of the entire voltage range, or the Thevenin's voltage range for the time delay? Since we are looking at 50% of the voltage for the time, right? For the time difference. Let me draw it. It's a really simple question, but I'm just trying to show you. So originally, what we talk about is, for example, this is the input, right? And this is the output. And the definition of the time delay is we define the 50% of the voltage range, and then we find out the time as these two nodes. So we define this time period as the time delay, right? However, for this Thevenin's equivalent circuit, we convert it to this. But if we run the simulation here, the DC voltage is getting divided. So eventually the VL DC voltage is only 50%. Does that make sense? This voltage can never reach Vin because of the voltage divider, right? So if we simulate this circuit, what we are getting is this and this, right? Agree with that? So you are looking at 50% of the Thevenin's voltage, which is 50% of this guy here. Okay, you are still using the 50% of the Vin. You are looking at here, right? Which is wrong. So you're looking at 50% of the Thevenin's voltage instead. So what about the rising edge here? 50% or 25% or somewhere else? So 50% here doesn't make sense, right? We can directly draw a line because they all reach the same voltage. But for the input rising edge, what time should we use though? Does it matter? You want to find the time, right, to compare to the 50% voltage time here, so you can define that time delay, right? So it doesn't matter where you define the time for the voltage for the input rising edge, like 50%, 25%, or somewhere else. Yeah, ideally, it should be 50, but it doesn't matter. You know what I mean? It's a super sharp. The input is considered as infinite, so it's just such a steep rising edge. So it doesn't matter. It's 50%, 25%. It's just all of them are at the same time point. So it doesn't really matter. You only look at this guy. Okay, 50%, and all the points on this edge will be the same time point. So it doesn't matter, right? So you can do that kind of calculation here. Another thing I want to talk about is remember. Let me type it somewhere. I didn't bring the camera. I type it here. Type. Okay, make it bigger. Right, remember the this curve, okay? It is VCT equals Vin times 1 minus this parameter, right? Minus T over RC. Okay? So this is the behavior of this circuit. So 1 minus is a constant minus a attenuation factor like this. Okay, so it shows a curve in this way. But remember, when we are studying that natural response, which is just a capacitor discharging through a resistor, and that natural response curve of the VCT discharging over time, so the voltage looks like this, remember? Right? Just to kind of recall this. Right, and this one equals VC0, right? Original voltage stored in the capacitor times E minus T over RC, right? So that's times this attenuation factor over here. Okay? If you use a constant minus this curve, eventually it's gonna flip this curve this way. Does that make sense? If you use a constant minus this curve, eventually you are getting a curve like this. And that is why when you are having 1 minus E to the minus T over RC, and this times VC0, okay? And you are getting a curve like this. It's just a flipped natural response curve. shows the time delay behavior for digital circuits. Just a really quick comments, okay? So know what's really going on. Why it looks like this, okay? Why it's charging up like this? It's because it's a constant minus this attenuation curve. So it's flip it to the top. So that's why it's showing this kind of behavior, right? For simulation in LT Spice, because all these Spice code is already provided, so you can directly run the simulation, and it should directly show this. But one thing I'm gonna let you guys know. Please modify your simulation environment a little bit, okay? In your PDF, I'm gonna take points off if you don't follow, okay? If you just copy and paste all these super dark background simulation files and all the curves are invisible, I wouldn't be able to give you the credit. You know, your super thin and light curves in the simulation in the black background won't be visible. Just let you guys know. So it's a really bad default simulation setting for LT Spice. So the thing you can do over here is this is recorded. You can always come back and see how I did it. So definitely come back. Let me run a really quick simulation first. Let's see how I can do it. Okay. All right, just start a circuit. Test.txt. Okay. Show you how I'm gonna do it. So the first line, if you are starting from the script, the first line is always a comment, right? So let's say test 1, and I'm doing vin, which is geez, I have to code up every single thing here. So let's don't use spice code probably. Too much coding here. Takes too much time. So I'm gonna just directly start a new schematic. And I'm gonna draw this guy. RC circuit. Connect it to this. Advanced pulse, initial value 0 up to 5, time delay 0, don't delay, it doesn't have to delay anything. 100 picoseconds for the rising edge, 100 pico for the falling edge, and T on to be, let me see what I used here. See, T on is 2 micro, 5 micro for period, 2 micro, 2U, and 5U. And that's it for the pulse. So that's gonna be the signal for the voltage. And resistor value is, let me see what I had here. So that'll be 1R. So 1R is that 5K? So these are 10Ks. So 1R will be 5K. So let's do 5K here. And the cap was 10 pico, I guess. No. 10 pico. Capacitance. All right. So when you're trying to do the simulation code, why do I have to delete? Yeah. Should be fine. All right. Okay. So you have to create a spice code for the simulation. Let's do a transient analysis. T.tran for, because you can look at the period is 5 microseconds. Let's just do like 10 simulations maybe. That'll be 50 or 25 will be fine. 5 will be fine as well. So you don't have to have all these parameters in there. You can either use like simulation from 0 seconds to 25 microseconds, and every 0.10001 microseconds to plot 1 point. You can give all the details, or if you don't specify it, it's gonna directly plug in the automatic numbers, the default numbers into it. I'm gonna just use transient analysis for 25 microseconds. which is fine. Okay, just using the default values or resolution, so you can run the simulation. Run a simulation. You can see the background is white. It's a light color, which is more visible if you plot any curves on it. So how to set that up? Which is go to Tools, Settings, and Color Scheme. And you can find out there are all these options, and you choose backgrounds and give 255 for the RGB values. So it's gonna give you a light color, the white background, and you can change it when needed. But in this class, please just use the white color. Okay, it's more visible. I can tell what's really going on. And for grid, I don't have to specify that. And for axis, right? So you can see my axis is a dark black color, so you can see the labels and the values. So make sure it's dark on the axis and values and labels. Okay. And for traces, it really doesn't matter. For like trace, you can specify 12 different traces. But for example, the first trace to plot is black, which is good. So black on white is gonna be super visible. It's great. So please use that combination. And for the second one, I think I chose blue. So you can see it's blue. So blue color becomes 255, and all the other two colors of the RGB are zeros. Okay. The third one, I got red. The first one doesn't really matter since very rarely I'm gonna have so many signal lines. So usually 3 will be enough for most of the simulations. So definitely set up that kind of property for the color scheme. And you don't have any signals yet. You can either probe it over here. You can see the outputs, inputs. You can see the traces are pretty thick as well. Very easy to look at. And I don't think I set up the traces thickness. So you want to go to settings and go to, for here, for font point size, I chose 20 and bold font as well. And for data trace width, I pick up 4. So it looks like so nice and easy to tell the values. Cursor width doesn't really matter. Anything else? Let's see. Schematic. There are some settings for schematic, the font size, the symbol size, and all these kind of things. Doesn't really matter. But I think the backgrounds keep it white as well. So making the traces of the schematic very visible. All right. So now you have all these signals plotted in the window, and you can left click and drag. Okay. So you can double click one signal line to bring up two cursors. Why do we need the 2 cursors? Because we want to calculate the difference. So here's one cursor, another cursor, right? 2 cursors. So I'm gonna point the first cursor or the second cursor, doesn't really matter, to the first rising edge, and the second cursor, when moving it, I want to look at here. So this one should show a 2.5 volts, which is 55%. It won't be exactly 2.5, but I'm getting 2.5043. It's very close to 2.5. So it's good enough. And then I'm looking at the corresponding T's. Okay, you can see the horizontal time for the first cursor. For the second cursor, and it's really nicely showing that the horizontal difference, cursor 2 minus cursor 1, even though it's a negative value, which is fine because you probably just want to see cursor 1 minus cursor 2. You are just looking at the absolute value of this time difference. It's showing you 38.59 nanoseconds. That's the simulation value. And you want to compare it with your 0.7 RC calculation. So it should match, right? Wouldn't be exactly the same value, but this should be very close. You'll do a quick calculation. Okay, 7 times 5 will be 35, right? And adding all these zeros, so 35 versus 38 is very close. So it's probably 35 nanoseconds in theory in the calculation, but showing 38 nanoseconds in the simulation. So you can call it, it's a match. It matches. The calculation matches your simulation. Any questions on this? Okay.
So, wait, just one more time. You double click it to bring up the two cursors?
Yeah, you click it twice on one signal line. So there's no way that I click this one, I want to bring up one cursor, I click this one more time, I want to bring up another cursor. No, it's not going to work. It's always, if you just one single click will only bring up one cursor, all right? If you want to bring up two cursors, it has to be pointing the same signal line. Double click, two cursors. Also, it's pointing to the same signal line, but you can still use it to look at time domain. You know what I mean? Both of the cursors are following the black trace. You see that? Both are following the black trace or the output trace right now. But the thing is, it doesn't matter. I can point it. I can just move it to overlap with the input. So it's pointing to the initial value with the rising edges time. And I'm going to move the second one to the 50% of the output voltage. So I can find out the second time point and do a delta t over here. Okay? And can you change the name of the signal line? Yes. So if you drew the schematic in LT-SPICE, you can define the signal name by giving a name here. Like say Vout, Vin. I have to run the simulation one more time, right? And then right click and add traces. So another way to add the traces. Right click at the window and add traces. So add Vn, Vout. Okay, that's another way to do that. So it's showing Vout and Vin this time instead of V N001, 000, things like that. So it's giving a name to it. So you can right click and add traces, or you can directly probe. You can directly probe it. Okay? You can directly probe it. Double click to probe it. However, in your design, you are not directly drawing the schematic in LT-SPICE. However, you are drawing the schematic in electrical VLSI. And eventually, like when you click simulation in electrical VLSI, it directs you to LT-SPICE. That's how that works. You'll see that later. Okay, so you set up a link. Where did I do that? I did it here. It's like a nested tutorials. One tutorial has a bunch of links to another 10 tutorials. So see, this one has a tutorial on how to set up LT-SPICE to electrical VLSI. So you just have to find out the path to your LT-SPICE and put into the SPICE software setting for electrical VLSI. So whenever you click simulation in electrical VLSI, it will directly open up LT-SPICE. So you are not opening up LT-SPICE like what I did over here. No. You are click the simulation button in electrical VLSI, which is over here. Tools, simulation SPICE, right SPICE DAC, boom, it should bring up this window. It opens up LT-SPICE from a different mechanism. So in that case, you don't have a schematic. So you cannot double click and probe it because there's schematics in electrical VLSI, which doesn't allow you to double click. So what's being brought into LT-SPICE from electrical VLSI is something called a net list, or SPICE code. It converts everything to the netlist or SPICE code and being put into LT-SPICE and run the simulations. You can see it's written on this day by electrical VLSI, this version, and this SPICE code. Okay, and then it's gonna open up this simulation window because you have the SPICE code in electrical VLSI over here. And this one opens up this window, and what you want to do is right click and add traces, because you cannot double click since there is no schematic. So you want to right click this window with a light color background window. Okay, 5 points off if you have black color background. One more time, so I've seen all these super dark background with all these invisible traces in there. Couldn't tell. Okay. Right click, add traces in it. Show really nice names. V in, V out makes perfect sense. Visible labels of the axis. Clean and nice. Right. And the second step is draw the DAC. So replace the ideal DAC with your resistor string DAC and rerun it. Okay? So when you rerun it, it should show the same simulation result. And eventually ground all these signals and run the RC circuit time delay verification. That's it. Any questions? Good? Yeah. Should be a very simple lab. Lab 1 for the first week, right? Okay, can start working on it. So this is not a teamwork, it's individual work. Submit individual lab reports to Canvas. Okay?